Welcome to Advanced Functions MHF4U 1. This is Exponential and Logarithmic Functions chapter. In this lesson number 7, we're going to pose and solve problems based on applications of exponential and logarithmic functions. So we're going to take a closer look at word problems in both exponential and logarithmic settings. First, we need to understand what is exponential growth and decay. So I'm pretty sure you guys are familiar with this from the previous chapters or last year, that exponential growth and decay may be modeled by using this form. Okay, so before I was using y is equal to a, b, x. It's same thing. So y is the amount of time, the amount at time t, so which is the final amount. This is y. And a, in this case a0, is the initial amount, makes sense. And b, same thing, b is the base. And x, in this case, represented as kt. Now remember I said x before, it was t over d, d representing, let's say, a doubling period, and t meaning the given time. So in this case, it will be t, which is a time, and k is a constant depending on the application. So for example, application meaning, is it doubling or is it decaying? So if it's doubling, then it depends. It gives you the doubling period, doubling every 2 hours or 10 minutes, or it could be decaying, like half-life, for every 10 minutes or every 1 hour. So it all depends on what the application of the word problem is. So in this case, we're starting from initial amount at a0, and exponential growth, it's increasing, and exponential decay is decreasing. So it's like looking like this. This is exponential function when the base is greater than 1. Okay, and exponential decay looks like this, where the base is in between 0 and 1. Common ratio. So we talked about, for linear relation, the first difference is constant. Quadratic, we found out that second difference is constant. And now, if we're looking at exponential, for exponential, the ratio is constant. Okay, so the exponential growth function form a geometric sequence. So geometric sequence is y, the second number, over y to the 1 is going to be the same. It's going to be constant. Okay, and given when x and x2, the values of the x values are in arithmetic sequence, meaning it's increasing at the same number or decreasing at the same number. Okay, so keep in mind, if you want to look at the table of values and see if it's exponential or not, look at the ratio and see if it's constant. Then if it's constant, that means it's going to be exponential graph. Now, developing exponential growth formula. So this is usually done for example, like compounding interest question, where AT is a final amount, A0 represents like a principal amount, your initial amount, and R is the ratio, the interest rate, rate in percentage, but you have to change it into decimal, and T is the given time in years. Okay. So this is another equation that you can look where if you're given a period of time and it's increasing by b times, so for example, doubling or tripling, then you will be using this. So this is usually used for like an amount, like dollar sign, or we could talk about like the bacteria or the doubling period. This is where we use. Okay, so two different formats that you can use, but essentially it's representing the exponential growth when the base is greater than 1. So let's do some practice questions. So question 1. For each case, find an exponential function that model the best situation. The value of the house is increasing by 7% per year. So we could say V at t, this is the value of the house after given time, is equal to the initial cost of the house, 1 plus 7% is 0.07 given time. So Vt is equal to initial 1.07 t. Okay. Next, the number of bacteria double every 5 hours. Okay. So we could say the number of bacteria. We could use y is equal to, we don't know what initial is, so let's say a, but we know it's doubling, 2, and then every 5 hours, so it's going to be t over 5. Next, now what about decay formula? So exponential decay, meaning decreasing. So there's two formulas again. Okay, so this is where the base, you'll notice that it's in between 0 and 1. And this is usually for, this is for a dollar, and this is for the number of bacteria. Okay, this specific example is when we are using half-life. So half-life, in this case, the base is 1 over 2. Okay. Okay, so let's try this. So letter A. The value of a house is decreasing by 5% per year. So it's decreasing. So it's an exponential decay. So we could say the value of the house, so V given time, is equal to initial cost of the house, 1 minus 5% is 0.05 given time. So I could simplify this. So it's going to be V0, 0.95 t. So it makes sense because my base is less than 1, so that means it's going to be decreasing. Letter B. So luminosity decreases 3 times for each 10 centimeter of depth. So I will talk about the luminosity formula in just a minute, but let's say luminosity, the final luminosity depending on the given time. Okay, let's say hour, and then luminosity initial, and so it decreases 3 times, so that means it's going to be 1 over 3, 1/3, and then the depth we're looking for over each 10 centimeter depth. So every 10 centimeter it's going to decrease. So the given the luminosity for every depth is going to be 10. And that will be your final answer. So a $150,000 yacht depreciates, so meaning it decreases 10% per year. So how long, so we're looking for time, does it take for a yacht to be worth $96,000? Okay, so it looks like we're given, so it's a depreciation, so we could say the amount is equal to initial 1 minus the rate given time. So we understand that it's going to depreciate. So it's going to decrease. This is my final amount. And this is my initial amount, which we bought it for. 1 minus 0.1, 10%, right? And then t. So I could simplify this, which is 0.9 t. So I'm going to move this to the other side, divide it. So it's going to be 0.64 and then 0.9 t. Now you will notice that it's hard to equate it. So what I'm going to do is I'm going to log both sides. Log 0.64 equals log 0.9 t. Then I'm going to bring t to the front. So log 0.64 equals t log 0.9. Then I'm going to bring log 0.9 divided so I can isolate for t. So t is equal to log 0.64 over log 0.9. When I do that, I get approximately 4.24. So therefore, how long does it take for the yacht to depreciate to 96,000? About 4.24 years that it's going to take to depreciate. Now let's go over some ideas of sound level. So sound level, it's usually usually done in opposite of exponential, which is logarithmic form. Okay. Now, so L in this case represents the soundness in decibels. And in this case, the letter I represents the intensity of the sound. Now, I0, which is the initial amount, is a constant, 10 to the negative 12 watts per meter squared. This is the intensity of the sound at the threshold of hearing. So it's a given number. Note, you could rearrange it in terms of L, which is the soundness, as the final minus the initial for the sound difference. Okay, so this will be the sound intensity in a given sound, and this I initial is the intensity of barely audible sound. Okay, barely audible. Okay, and L represents the loudness in decibel. So decibel symbol looks like this. Okay, so let's try incorporating this word problems, the understanding. So Joyce claims that she was in an earthquake that was 125 times as intense as one that Mark was in, which measured 5.2 on the Richter scale. What was the magnitude of the earthquake that Mark was in? Okay, so this question, it talks about how much times it was loud by, which is 125 times. So this, you don't have to necessarily use the decibel scale. We're going to use a proportionality. So we could say 125 times it was loud over 10x, which is the magnitude of the earthquake. And then for Mark, it will be 5.2. Okay, so we should say, let x be the magnitude of Joyce's earthquake. Okay, so this, right now what we're doing, rather than using a decimal scale, like I said, we're given how much intense the sound was. So we can use a proportionality. So this, the numerator represents the Joyce, and you're comparing to 10 to the 5.2, which is what the mark was in. Okay. Now, so what we can do, after we set up the equation, we could simplify. So we're given a same base. So 125, we could put it together, x minus 5.2, the exponent law. Okay. Now, we have variable in the exponent, and we can't really equate it, right? Even with 5. So what I'm going to do is I'm going to take log to the both sides. So log 125 equals log 10 to x minus 5.2. Then I'm going to bring exponent to the front. Log 125 equals x minus 5.2 times log 10. And then I'm going to bring log 10 to the other side divided. So log 125 over log 10 equals x minus 5.2. And then, so simplify this, and I'm going to add 5.2. Okay, so let's bring this to the other side by adding. So you will get x is equal to 2.096 plus 5.2. X is equal to 7.3. So therefore, what can you state? That Joyce was right. So Joyce was in a 7.3 magnitude earthquake. Now that's a lot, earthquake. That's a very strong earthquake. Very, very strong. Okay, good. Okay, now this time. So how many times, so this is a different question. So how many times louder is a stereo measuring 97 decibel than a conversation measuring 43 decibel? Okay. So now we're given a decibel question rather than like how many times in terms of proportionality. So what we could do is first, let's write down the formula. The loudness is equal to 10 log I over I0. So first thing we need to do is we need to figure out the loudness for each thing to figure out how many times. So first, stereo. And then I'm going to find the loudness for conversation. So for stereo, the loudness is 97 equals 10 log I over, we know I initial. It was given 10 to the negative 12. So after we write down the given information, I'm going to bring 10 to the other side. So divide it, so it's 9.7 equals log I over 10 to the negative 12. So what we can do after is we can take the base of 10 to both sides. Okay, so what we could do, 10. So what we could do is take the 10 to the both sides. It's the same idea of taking log to the both sides. 10 to 9.7 equals 10 to the log I over 10 to the negative 12. Okay. Now that we've taken 10 to the both sides, what do you notice? We're given the same base, 10 and 10. So if that's the case, then you could simplify by getting rid of the log. So it will be 10, 9.7 equals, it cancels out, right? Because it's same base. It's I over 10 to the negative 12. And then I'm going to move this to the other side by multiplying. I is equal to 10 to the negative 2.3. Okay, So that is the intensity for the stereo. Now for conversation, same thing. So it's going to be, so we can skip all this to this step. Very similar to this. Because we will be taking exactly the same as taking the log and then taking the base of 10. So it's going to be 4.3 equals I over 10 to the negative 12. So bring this to the other side, you multiply. I is equal to, the intensity is 10 to the negative 7.7. Okay, so let's figure out how many times louder is the stereo. So therefore, the stereo has to be the numerator. Loudness, it's going to be 10 to the negative 2.3 over 10 to the negative 7.7. Therefore, when you simplify, it's 10 to the 5.4. So it's about, I would say, 251,188.6 times loudness. That's really, really loud. Can you believe it? So in terms of decimal, it doesn't seem like it's going to be loud enough, but when you compare it, the stereo is 251 times 251,188 times louder than the conversation. Okay, so it's very, very exponentially bigger. Okay, so lastly, we have pH scale. So we use pH scale in chemistry very often. So pH scale, it is a measure of acidity or alkalinity of a substance. So that means acidity means acid. Okay, alkalinity is the base, alkaline stability of a base. And it measures the number of hydrogen ions in a mole of a substance. Okay. Now the scale, the pH scale, it ranges from 0 to 14, and 7 being the neutral. So 14, the bigger the number, it's going to be basic. The smaller the number, closer to 0, is going to be acidic. And 7 is the neutral. Now, to find the pH, pH is equal to negative log N. N in this case is the number of hydrogen concentration, so I could rewrite it. pH is equal to negative log to the hydrogen ion concentration. So this is a formula that you have to remember. So the purpose of it is to figure out, is my substance acidic or is it basic? Question 6. So determine the pH of a solution where I'm given hydrogen ion concentration of 0.0047. Okay, so let's rewrite the formula. pH is equal to negative log hydrogen ion concentration. So negative log 0.0047. And when you punch that in your calculator, you get 2.3. That is my pH. So what can you conclude about it? It's very acidic. It's close to 0. So the lower the number, the acidic the compound is going to be. Okay, another question. So determine this time the hydrogen ion concentration when you're given pH of 2.4. Okay, so it's the opposite again. So let's rewrite it. pH is equal to negative log hydrogen ion concentration. So let's plug it in. So 2.4 is equal to negative log hydrogen ion concentration. So what we can do is divide negative to both sides. So negative 2.4 equals log hydrogen ion concentration. And then let's put it in exponential form. So 10 to power of negative 2.4 is equal to hydrogen ion. And when you punch that in your calculator, you get 4.0 times 10 to the negative 3 mole per liter. So this is how much hydrogen ion is in a pH of 2.4 solution.